Thank you, Bob. I didn't realize this is going to be streamed, so I'm a little bit nervous. But anyway, good morning, everybody. My name is Kenji Rikitake, and today I'm going to talk about the ham radio and how ham radio data would be processed with our product, Riak. So the title is called Amateur Radio Propagation Analysis with OTP and Riak. And these are my call signs. You don't know what the call signs, whatever, but these are the national, international identifier on my ham radio stations. So first of all, if you don't have time, just check these executive summaries. I'm going to talk about how amateur radio has turned to be a sort of sensor networks. Every station could be a sensor, sensing other radio stations' transmissions. And those reports are gathered into a hub, a big hub, somewhere in the world. And it will be a part of big data archives. So when you transmit something on the ham radio, you have to be very careful. You have been warned. And it's still less than 2 months from when I started working for Basho. So this is this is a training exercise report of some sort of a big data with our product of course Riak and a new search engine called Yokozuna. And my conclusion about this experiment is that Riak with Yokozuna fits very well for data analysis. This is a sort of obvious conclusion, but if you doubt about this, just try it. Yokozuna can be built pretty easily from the normal Riak GitHub repo. So, and if you have experience with Apache's Lucene or Solar search engines, that'll be more easier. Okay, first of all, let's talk about what the amateur radio is. Amateur radio on the FCC rules in the American law. I'm going to talk about the American law, though in Japan there will be a different rule set of law will be applied. In America, amateur radio is defined as a radio communication service for the purpose of self-training, intercommunication, and technical investigations carried out by the amateurs, that is, duly authorized persons interested in radio techniques solely with a personal aim and without pecuniary interest. This is a so big word, so I'm going to summarize this. You can transmit signals when you pass ham radio's exams in certain frequencies. You can build your own transmitters. You can erect your own antennas, and you can communicate with the people at other amateur radio stations. But two important things. Number one, you can't do any business. You cannot talk about money over there. If you are doing business on amateur radio, your license will be revoked, and you'll be fined from FCC in the United States. And the second one is that you have no privacy, absolutely no privacy on amateur radio. So what you transmit on your amateur radio will be recorded or used or abused or even rebroadcasted or used whatever in any form. So let me talk about the historical perspective on the amateur radio. Ham's role in technology. Yeah, hams, they do love chatting. And the only thing they do on the air are chatting. Chatting with Morse code, chatting with computers, or chatting with microphones. And on the airwaves, they're actually the ancestor, I should say, the ancestor of online chatting culture. And the good thing about amateur radio is that amateur radio is open for everyone. You don't have to have any certain kind of certificate before taking the exams of amateur radio. So there are lots of ordinary people have joined the amateur radio community. In the United States, there are approximately about 700,000 or even more amateur radio station call signs are licensed. And there's a code called Morse code. It's a very primitive type of the digital signal. Like when you say ABC, you say it D-da is A, da-di-di-di is B, and da-di-da is C. And these are the original, I say the original digital, because it's invented in more than 100 years ago, and it's still used not for the professional communications anymore, because all the seamen now use more sophisticated systems. But it's still being used in the military, and of course it's still being used in amateurs. And amateur radio has played a role of emergency backup communication, and there are lots of volunteers, at least nationwide, in this country, United States. And there will be some in Japan, but I find the most active country about the emergency communication is in the United States. And amateur radio has contributed a lot for disseminating electrical and electronic technologies to the general public. For example, yesterday I got the tutorial from the Erlang factory from the Erlang Solutions Omero, and he taught us about the Raspberry Pi. And that kind of thing were previously done by ham radio communities. And some hams in the United States are now interested in Arduino, or maybe some of them are already tackling into Raspberry Pi, or maybe Erlang. And ham radio ops are the ancestor of nerds and geeks and etc., these cultures. See, this is a German amateur radio QSL card. QSL card stands for card of confirmation, or the greeting card that to prove that you and I get contact with each other in a certain timing of the certain timing. And you will not immediately understand what these people are doing with these strange type of equipments. These equipments are actually radio transmitters and receivers. And this is me, a little bit fatter than now. It was 2004, and I wanted to took a picture look like this. And these are my equipments. Actually, I had telegraph key and radio transmitter device and other gadgets like this, and with my Japanese call sign here. So this culture, amateur radio has the virtually same culture, although the one sad thing I got to reveal is that the community is aging so higher than our culture and our culture of our developers. Okay, back to the explanation of amateur radio. I repeatedly told you amateur radio has no privacy. There are some examples about the law in the United States. First of all, you must identify the call sign at least every 10 minutes, or at the end of the communication. When you say goodbye, you have to identify that this is N6, this is November 6 Bravo Delta X-ray, or something like that. So you can't be anonymous. And maybe somebody in the FCC will be listening to your traffic. You're wiretapped. You're wiretapped as default. And your mailing address is open in the FCC's database. Every licensee in the United States, including me and other amateurs, their mailing addresses are open. Even if there are PO box address or some residential address, they are open. So you can't hide. So if you do something brave under your call sign, you should be careful. Somebody else will locate you and do you something very bad to you. Okay, and the third thing is that there's a law of the 47 Code of Federal Regulation, number 605, section A. It says that the content transmitted over amateur radio is not protected by any law. So this can be used, disclosed, and analyzed for any purposes by any means, by anybody. So by this characteristic, you can use the information got together from the amateur radio for data, training data of training data for the data analysis. So there are many kinds of contents I'm going to introduce to you from now. But before that, let me tell you about the how airwaves propagate. I mean, for example, the shortwave. Shortwave does not necessarily directly propagate from this antenna to this antenna. It will go up into the air and will be refracted through the ionosphere and bending back to the ground like this. So by this characteristic, you can for example, you can communicate from Japan to the South Africa or some part of Brazil or anywhere in the world, Antarctica or whatever the named islands with very, very unfamiliar names or whatever. And this ionosphere is a natural phenomenon. So it changes. It changes as magnetic disturbance occurs, or the change of solar activities, or lots of other factors. So scientists are actually measuring how these ionospheric behavior change. So let me tell you about some tools of the amateur radio, how to get the digital data from amateur radio traffic. This is a software called CW Skimmer. CW stands for Morse code. And this software actually skims the sound from the sound input, and it decodes all the continuous stream of dits and dots, and decode it to the actual call sign with the software of the also says using the Bayesian statistical analysis. And sometimes in a very crowded band, there will be 100 or 200 or many, many stations under the bandwidth of narrow bandwidth of 10 or 20 kilohertz. So, and the good thing about this is that when you transmit, what you transmit on your hand key will be detected by computers, and it will be sent back in the central server. And the central server is called reversebeacon.net. There's a notion of the word beacon. A beacon is acting like a lighthouse. It sends periodic signals for measurement. And reverse beacon is that all those stations around the world gathering the information by listening to the signals with the automated facilities and sending those reports to the hub system for the data collection. So lots of stations running CW skimmers are sending data back to reversebeacon.net domain. And each report includes the location of the reporter and the reported station. This is the location, and this is the reporter, and this is the reported station. For example, this has the locator is in Namibia, and it locates a station transmitted from Hawaii. You can identify those information from the prefix of the call signs. And there's a frequency information in kilohertz. It's about 140.177 kilohertz right here, and including signal strength and the transmission speed. This kind of information are all collected automatically 24 hours a day. And there's another type of protocol called Whisper. WSPRnet, it says Whisper. And this is a very low bandwidth protocol. It takes 2 minutes to send only 50 bits. The speed is only 1.5 ball. So, and it sends 162 symbols, takes 110 seconds. And the bandwidth is very, very small, only 6 hertz. And by this characteristic, this, you can use it as a telemetry system. For example, this is my antenna at home. I live in a condo, and the length is about 6 meters or something like that. I put this antenna with a fishing pole with wire. And I put 5 watts of electrical power inside here using this protocol. And I often confirm that my signal reached to Norway from Japan with only 55 watts. So with the help of computers, everyone can hear you. And the report will be get together to the, there's a site which I will explain next called WSPRnet. And this protocol is designed by a Nobel laureate who happens to be another amateur radio enthusiast called Professor Joe Taylor. And his idea about the synchronization of this protocol is very simple. You just send the airwave from every first second of the minute. So you don't have to synchronize using the signal. You just use the absolute timing. And this is the kind of very ad hoc protocol, but it works very well. So let me talk about WSPRnet spot database. And you find a transmitted call sign. Those begins with K and W are all in the United States. This begins with Z, and it's in Great Britain, or better say United Kingdom. And this DC stuff is from Germany. And yeah, those kind of stations. And the frequency is measured on the order of hertz, 6 digits or 7 digits. Not all stations have this accuracy, but technologically this is feasible using temperature-controlled crystal oscillator or something like that. And the reported call sign is also listed. And some people doesn't have the call sign. I mean, they don't have the legitimate license. But they can send a report because listening to the radio or airwaves, you don't have to have a license. So there's a signal called, there's a pseudo call sign called W17987 over here. And there's another string called grid. Grid stands for a certain kind of encoding of latitude and longitude of each station. So when you give a grid string, for example, somewhere in Japan, PM 74 or something like that, that will be converted into the location around the 35 degrees north, 35 degrees north of latitude and 135 degrees east of longitude. So with this information, WSPRnet calculates the distance, and azimuth means the direction of the wave, how it propagates. So to summarize this, this kind of information is also automatically collected and gathered and has become a big data. And this is a real-time snapshot of a real-time propagation map. Lots of traffic between the Atlantic, and very few, but some exist in the Pacific. And there are traffic between Australia and Asia, or Europe, or even in South America or Africa. So this is a pretty trivial application of mapping those data into Google Map. So let's talk about how big is the data. About the reverse WeakNet, I'll show you the actual data examples. But about reverse WeakNet, it's about 171 million records gathered for past four years. And for the WSPRnet, 125 million records gathered for past 5 years. And I actually downloaded them all, and measured the size. And it's 4 gigabyte compressed, and 21 gigabyte when uncompressed. That's the CSV data, CSV files. So can RDBMS scale well for this size? I don't know. Maybe they will if you give a bunch of memory, like 128 giga or 256 gigabytes. But maybe not for laptops. So so I decided to use Riak. There's a little bit of disclaimer. You can see it on the slide. You can see it on the slide. But I got to tell you, I'm a bachelor employee, so my view might be biased. But I try my best not to make this a sales pitch. So why Riak? It's written on OTP, and I've been touching on OTP for the past 5 years, and I know how it behaves. And of course, we are in our factory, aren't we? So I'm trying. I like to talk about the Erlang software. And it's what I've been working for since last month, February 2013. And I got to tell you, I'm a newbie. I'm a newbie and noob about this. So I'm still learning a lot of things about it right now. So contents of this presentation may be far from complete. So I welcome your feedback or comments. The good thing about Riak is it's open source. It's open source. Nothing to hide. You can try it by downloading this repo. And recently, our sibling product called Riak Cloud Service has also become open source on the 20th of March. So lots of things Bachelor provides as open source. And it scales. It scales very well especially when you try to handle a lot of data. If you use Riak or any other kind of database which has the characteristics of distributed storage, you can prototype in a very small data set. Yeah, trying first by a small subset of data set, and deploying it to the larger data sets is very easy. So that's what I tried to do in this presentation. And before doing the whole thing, I tested a few strategies of the database structure. First, I just made Riak as a crowd, not a crowd, a distributed storage. And just putting those files on the Riak and trying to analyze on the external clients. There are advantages and disadvantages about this. Advantage, this is fast. Lighter load on Riak servers, but the disadvantages is that the clients have to search individual CSV files by themselves. So this is kind of a no-brainer solution, and not really get the most out of the functionality of Riak. So I decided to choose this one, storing each event record with indexing. By adding index to every data or every line of CSV by the Riak, advantage is that it's searchable, and it's even searchable pretty easy as if using an SQL DBMS with a simple search commands. But it also consumes a lot of CPU power on the Riak side, and it will cause a heavy load on those servers for the pre-processing. I mean, in the technical term of Riak, it is called pre-commits and post-commits. But anyway, I chose strategy B of storing each event record, because Riak has its own search facility called Riak Search and Yokozuna. And Riak can handle JSON as a native data type. And JSON is very easily convertible from CSV. And I got to tell you the truth that there's very little time was available for prototyping external programs, maybe 1 or 2 days. So I got to do it very fast. And I also had a personal interest that I wanted to explore what I can do with Riak alone. So let me show you about the data I'm going to process. Oops. Sorry. No, I don't want to get exit. Sorry about that. Oops. 6, 5, 4. Yep. This is the raw data of a reverse speaking entry. It's just a plain CSV file writing down load entries. And you can see you have already seen this as a part of the slide. And for the WSPRnet, the timestamp is different. This is actually Unix time, Unix time seconds, long integer, 32-bit integer. And this is also a CSV file. Nothing special about this. So let's get back to the slide. Right. So let me explain about my testing platforms I used. The testing platform is my good old laptop, which I also use for the Erlang Workshop 2012 presentation. It's a very typical machine. i5 Core i5 quad-core CPU with 2.3 gigahertz clock. It has 8 gigabyte RAM and 500 gigabyte hard disk. And it runs FreeBSD. And it runs Erlang OTP R15B03. Unfortunately, this is not yet R16B because Riak is still not compatible with R16B. And I'd like to state officially, Bash only supports R15B01. So if you do the production release in Riak, using R15B03-1 would be of some risk. And I have a supplemental test environment. It's actually a MacBook over here. And actually, Riak is running right now while doing the presentation at the same time in this MacBook. So what I did first is to compile our own R15B03 with using curl. Curl is a utility which allows multiple versions of Erlang OTP instances, which is easily switchable for each shell environment. And I've tested curl on FreeBSD, Ubuntu, and OS X. In all of these environments, curl works marvelously, very easy. So if you have to switch over many versions of our instance, I suggest you use curl. And I installed vanilla Riak first and tried to run 5 nodes on just 8 gigabyte of memory. First, without data, it worked very smoothly. But as a lot of data is coming in, each instance has become, the data is more and more getting bigger, and maybe 500 mega or 1 gigabyte in the actual memory. And it causes swap space exhaustion. So I recommend you don't do that on 5 nodes if you really want to use the Riak on this type of system in a production system. So I reduced the node number from 5 to 3. So 3 seems to be a feasible maximum because Riak has a default parameter of W is 3. What W consists is that the number of copy to each node of an object to be made or to be stored on a Riak cluster. So if you set W equals 3, and when the whole cluster only has 3 nodes, everything will be copied to all nodes. So this will be robust. Although this could be slow on a real working system. So please treat this as just an experimental parameter. And next, I tried to test Riak Search. Riak Search has Solr-like interface, and it mimics Solr, a set of the command list of the search parameters. And Riak Search has its own conversion facility, JSON fields to searchable indices or indexes. In Basho, there's a discussion on which you choose, the indices or indexes, but people are now using indexes, whatever if it's grammatically correct or not. So I stick on indexes right now. And it's sort of CSV after converting CSV to JSON. And Basho has its own Python client. And let me show you the code. Whoops. Yeah, it's on this one. Yeah, all you've got to do is import sys, JSON, and CSV, and import Riak. And importing Riak, and you connect Riak to, yeah, this is a private host within my house. Private, sorry about that. And with the PBC, stands for protocol buffer communication. And you make the bucket. For those who haven't heard about Riak, and there's a terminology in Riak called bucket. Bucket stands for a key value database. A set of key value table is called bucket. And it's also a technical word for Amazon S3 database. And so you specify the bucket, and it's ready to get accessed because it's object-oriented programming language. And you define the fields like this. Call sign, or D means originating prefix, or some date. And I intentionally made this all as strings because for the string data, they will virtually accept anything. And you open the file here, and you read each record of the CSV file with this method, and you make a new object of B. B stands for here, right here, bucket. And you store. And you write a for loop, which is not familiar with, probably not familiar with ARM programmers, but you write a for loop, and you just close it. This is what it's all about, the storing data into Riak with the Riak Python client. And it's very easy. And the entire work will not take 20 lines. So if you try storing your own data of the CSV, just try a Python client first. So let's get back to the presentation. Oops. And before using Riak Search, you have to tell the Riak that we are going to use Riak Search on this bucket. So you have to build the index for each bucket before putting in the data. There's a command called search command install bucket name. This is a Riak command written in Erlang, and so you just do it, and you're all set for Riak Search. And I tested this for about 1 or 2 days, and this worked OK, but there were certain problems. It didn't implement full-range query, and it was hard to use for what I wanted to use, what I wanted to do. And it was slow and consumes a lot of CPU time on the Riak instances. And getting the number of each field member is unfortunately not well supported on Riak Search. And about the weirdness of Riak Search is that this is about process top screen, and this is a log average, a good old xload output. And the xload here shows what is on the idle cluster of Riak. And it's very weird that even Riak is doing nothing but maintaining its own cluster. In every 15 or 20 minutes, the roll average gets high from 1 to 3, and the CPU is high from 0% to 100 or something like that, and going up and down and up and down, up and down like this. And this continued for a while, for more than 5 or 6 hours. So I thought, I don't know. I actually don't know. I'm too newbie to know this, whether this is a bug. So I haven't filed in a bug report. Sorry, my colleagues. But this is not a normal behavior. So, so I decided to try Yokozuna. This is a new, still alpha stage or beta stage software. And this is a traditional Yokozuna of the sumo player. And Yokozuna in Japanese stands for the real champion. And the tsuna means the belt over here. And yokozuna, yoko stands for horizontal, this direction. So yokozuna is about this. So let's quit about the explanation of the original trivia. And well, yokozuna is all about it. It's a code name for the full text search engine for Riak with Apache Lucene. Lucene is sort of a proved technology of the distributed search in Java, and it's well equipped. Of course, it supports range search and lots of different things. And what is yokozuna is an implementation or wrapper of Apache Lucene or Solr. And it has on its GitHub repository. You can find it over here. And if you want to run yokozuna, you can try a branch of yokozuna in the Riak. It's on this YG merge 1.3.0. And it requires Apache Ant. This is a utility for Java, written in Java. And it's running, or it will automatically download the Solr utility. And when I tried this, it was 4.1.0, but now it's updated to 4.2, the latest version. And as in the Riak search, even on the yokozuna, you have to create an index and to tell the Riak or yokozuna to say that we are going to use the bucket. We are going to use the index on the bucket. So this is a more crude curl command. We're making a JSON index with the YG stands for yokozuna, YG index, and the name of the index. And by convention, name of the index is the same name as the bucket. So you put the bucket name here as a part of the URL. And for crunching the JSON records, each JSON record has to have the type of the content type as the application JSON. And to tell data type for each JSON field, you have to add certain type of suffixes, like -s or -d or -i. It's documented in source code of Riak right here. I'm sorry, source code of yokozuna right here. And of course, yokozuna is running on a Java utility. You have to install Java. Remember, not all systems are Java equipped. For FreeBSD, you have to compile the whole Java kit from Java OpenJDK like this. And for single thread entry, for single thread puts, sequential puts, the Riak server will not give you the maximum performance. So I used GNU Parallel as a parallelizing shell script of different files, putting different files simultaneously. This is the easiest way. So I recommend you to try this. And I also tested NIF for bitcask enabled, but unfortunately, this didn't make a big difference. Because the most of CPU time when you use yokozuna or even Riak search, they are consumed by the making an index for yokozuna or Riak search and sorting it within the RM beam. So probably indexing needs most of the CPU time. And I use protocol buffer used for the Python clients because it's more lightweight and more fast and convenient especially when you use a pile of small chunk of data. And since Riak is KVS, key value database, you have to make a choice of keys. And you can do either way, use a predefined key or let the Riak choose the key. And for my purpose of getting the stats of the CSV records, either way could be possible. So I just let Riak assign keys on the reverse beacon data. And for the WSPRnet, I use a unique key given in the WSPRnet. WSPRnet assigns every different unique ID for every different event. And I observed no performance usage change between the two. So you can use either way as you like. So the put test results is here. And despite I gathered lots of data, I could only manage to put only a total of 1 million records in the laptop here and at home due to the I think this is due to the processing limit of the performance limit of the Riak itself or Yokozuna or other operating systems. And I crunched about 500,000 or 400, about 547,000 or 456,000 of data of each set. And I also tried to do the backup. And it took 170 seconds for 2.24 gigabytes. And just for this backing up means reading the data from Riak and searching the old database through. So when you try to restore the whole stuff, it will take much more time. So you should try by yourself on a small set of data, and I recommend you to do that by yourself before just blindly trying to do the Riak admin restore. And the put speed is about 270 records per second. I don't know whether this is slow or fast, but the average, from the empirical values of the production cluster of Riak of 1,000 puts for data is considered fast enough. So 270 was not that bad value. And there are other things I should note that very heavy loaded Riak clusters, not serves, but this is a server, may cause timeouts. So if you are going to use write a client of your own and make sure that all Riak data to be put into the servers, you have to deal with the timeouts. And one thing I failed initially was to use the make Devrel option. Devrel copies all of Java archive files for each instance. So when you make a 3-node cluster, it makes a copy of 3 Java files, and this is not good. I suggest you to use instead make stage Devrel. This only provides symbolic link for the necessary files and only use 1 copy, and so this uses much less disk space. So let me talk about the query example right here, and it's telling about search and giving a bucket name here and return value with JSON and with indent on, and row 0 means that I only want numbers, no real data. And this is a query condition that about the band in megahertz will be 21. And there's a function called Faceted Search. This is a additional search method built in on the Solr, and you can get the sorted result of the value of the certain field under the query condition. So with doing this, you find this is a whole JSON result, and this is the number found, the records found. It's 3,890 right here. And there's a list of frequencies of each record associated. And for this one, it will be 4. This one will be 18. And I'm not going to describe it in numbers. I just draw it a graph. And it's something like this. I used R script, simple R script for this. And this shows that people tend to concentrate on the usage of each signal, and although the band allowed for this protocol is wider than this, like this. Okay, so I'm going to explain another example about reverse beacon, and I made about the continent analysis of where the spots are from and where spotted stations are, and I'll make it short because the time is running out. And with performing 6 searches, I could draw this type of data, and obviously, exchange between Europe and North America is higher than the rest of the world. So let me conclude this analysis presentation. The lesson learned is that if you handle the database, do start from the small data sets, because you can trust Riak or Yokozuna or whatever distributed database on handling very well on the large data. For the faster prototyping, the most important factor is how short how frequently you can do the trial and error. So the smaller data sets will be much easier to handle and consume less memory and less time. And I have to tell you that laptops are not as powerful as dedicated servers. So don't try 200 million records into a laptop. And the next thing I learned is that use the most suitable tool for each task. Erlang OTP is best for servers, and the strength of scalability, and there was no crash on Riak. I tell you, no crash on Riak in this operation, and that was very good. But when you try to convert some string data, Python has its own strengths, and why don't you use it? Just use Python for faster prototype. And when you try to analyze the result of coming out to JSON, R is a convenient system for plotting all the data. So last but not least, I'd like to acknowledge these people. Especially for Ryan Ziziski, the author of Yokozuna in Basha Technologies, my fellow colleagues, all those people, and who helped me directly during my preparation of the presentation, and all the DevOps of the Reverse WSPRnet and WSPRnet. So thanks a lot, and all scripts are here, and if you have any question, I'll take it. Thank you. One or two? Yep.
Did you try running just the one node on your laptop?
3.
Okay.
So
typical production configurations only have one node.
Yes,
physical.
Exactly. I just wanted to see whether Basha node would get down or up or something like that. Just for my curiosity. Of course, in typical production node, the best performance will be drawn when one instance, one node. That's quite obvious. Yep.
You use default recreation size, or was it 64 byte?
Yeah. That's a good question. I think I should have tuned to 256 or even more, but I used only 64 this time. Because I didn't have expertise of tuning, but for the real production system, you should tune it. You should tune it, maybe by trial and error. That's it. Okay, so thank you very much.